Hello, my name is Justin Sims with DANTE Solutions. My presentation today is titled Simulating Quench Hardening Processes of Steel Parts. As a quick overview, we will be looking at several heat treatment modeling aspects, including what is required and what is predicted, phase transformation and mechanical models used to describe the phenomena, and thermal boundary conditions. We will then examine several effects of various parameters on phase transformation behavior used by the DANTE models. We will then look at 3 case studies, which include scanning induction, hardening of a truck axle, press quenching of a bearing ring, and press quench tooling design. We will then examine the effects of phase transformation on distortion. To begin our discussion on heat treatment modeling, I first want to discuss what phenomena is required in the modeling of heat treatment processes. If carburization or nitriding is used, a mass diffusion model must be incorporated. For quench hardening processes, heat transfer for heating and cooling processes is needed, the stress and strain for prediction of deformation and residual stresses, and solid state phase transformations for the microstructural evolution prediction. The figure on the left shows these last 3 phenomena needed for the quench hardening process and the relationship between several phenomena, including the latent heat, temperature-induced transformation, volume change due to phase transformation, and thermal expansion. All of these are indicated with the solid lines and are absolutely required for heat treatment modeling. The other 2, heat generated by plastic deformation and stress-induced plasticity, stress-induced transformation, are of less importance during the actual modeling of the process. They have insignificant effects for the most part. The heat generated by plastic deformation, however, does need to be modeled if you are doing large deformation processes such as hot stamping or hot forging. The figure on the right shows the methodology used. Most heat treatment modeling is done with finite element analysis, and therefore meshing is needed on the CAD model. Carburization or nitriding is fed into the model first, followed by the heat transfer methodology, usually using heat transfer coefficients as the boundary conditions. Kinetics models and their respective databases, as well as the mechanical model and their respective databases, are then fed into the model using the carburization results and the heat transfer coefficient. The output then becomes microstructural evolution, dimensional change evolution, and residual stress evolution. The final hardness is also predicted. The figure in the bottom left shows the general form of the phase transformations resident in the DANTE software. They show the phase transformation behavior for the 3 diffusive transformations in ferrite, pearlite, and bainite, and also the diffusionless transformation, which is temperature driven, in the martensitic transformation. These parameters can be determined from dilatometry or TTT diagrams. However, dilatometry is preferred due to the additional strain information gathered, as well as the coefficients of thermal expansion. So there's a lot more information that can be gleaned from a dilatometry test than from a TTT diagram. However, TTT diagrams can work if need be. The figure on the right shows the internal state variable model, which is used inside of DANTE, the generic form anyhow. The properties of this internal state variable model must be a function of phase, carbon, temperature, strain, and strain rate. They also must include a mixture law, since at any given time one element can be made up of multiple phases. The internal state variable model is preferred over the general stress-strain relationship because of its ability to capture the hardening and recovery mechanisms which occur during the quench hardening process. The internal state variable model is also able to capture the stress reversals which occur much better than the stress-strain relationship which is generally used. The final aspect of any quench hardening model is the thermal boundary conditions. These thermal boundary conditions are just important as the models themselves, and each system can behave very differently, even identical equipment and model numbers. So it is highly advantageous to characterize these furnaces and these quench vessels to understand the thermal behavior of them before modeling them. However, generic values can be used to get us within the ballpark. For liquid quenching, the three stages of quenching must be described by the heat transfer coefficient: the vapor blanket, the nucleate boiling, and the convection. All must be described as heat transfer coefficients as functions of surface temperature. The figure on the left shows two heat transfer coefficients as functions of part surface temperature for a general oil flow and a stagnant oil flow. So reasonable agitation and no agitation. And you can see that we peak out at about 550, 575 C is where the nucleate boiling is at its maximum. You can see the vapor phase and the convection phase on either side. For gas quenching, it's a little bit different. We assume that the HTC remains constant, which is a pretty good assumption from experiments that we've conducted. However, the fluctuation in ambient gas temperature must be considered. So this is due to the figure on the bottom right. So this part comes out of a hot furnace and is then put into a cold quench vessel. So as the part is placed into the cold chamber, the ambient gas around the part spikes up. As the part is cooled and the heat exchangers of the vessel then cool the ambient air, then the temperature can come down. But this behavior will affect the phase transformation timing and must be considered. Grain size also has an effect on hardenability, as shown on the figure on the bottom right. The grain size of the figure on the bottom left is 63.5 microns, and the bottom right is 163.5 microns. The grain size of the material is affected by previous mechanical and thermal processes, including forging, rolling, normalizing, annealing, etc. The grain size does have a noticeable effect on the transformation behavior. And again, just like the alloy composition, knowing this is important in heat treatment process modeling. Effect of initial phase on phase transformation timings. The figure on the right shows two samples being transformed to austenite dilatometry samples. The orange line, the sample was in the annealed condition. The blue sample was a rerun of the first sample after quenching it with a fairly severe quench rate to obtain near 100% martensite structure. And you can see the volume shrinkage due to tempering that occurs at higher temperatures of the second sample. This initial phase also affects the AC1 and AC3 temperatures, as can be shown in the austenite transformation towards the top of the graph. So understanding the initial phase of the material is also very, very important in heat treatment modeling. The effect of the initial phase is also carried over to the martensite transformation strain. Here we have three graphs. The blue line is an initial phase of pearlite. The orange line is high temperature tempered martensite, and the gray line is low temperature tempered martensite. And you can see that it does not affect the MS at all. However, it does significantly affect the final strain in the sample, which will significantly affect the distortion of the part. So just to reiterate, understanding the initial phase here is of the utmost importance. So it's always wise to do micrographs of incoming material before modeling begins so that the initial microstructure can be understood. Rounding out the effects of initial conditions on phase transformation behavior is the effect of initial carbide on phase transformations. When I speak of carbide here, I'm speaking of primary carbides formed either during the steelmaking process or during a carburization process. So all the figures on the right-hand side with the red and blue curves show a total carbon of 0.8%. So that's carbon which is in the matrix or is easily dissolved. and carbon in primary carbide form. So the blue line represents total carbon. So you can see that we start out with 0.4% or 0.004 weight fraction and is then dissolved during heating and hold. And the figure on the top left, bottom left, and bottom right are all soaking temperatures of 850 with different size carbides. So the top left is medium, bottom left is small, and bottom right is large. So we can see that small carbides dissolve very quickly and totally, whereas the medium size almost dissolve completely uh, and dissolve at a slower rate, and the large ones dissolve at a very slow rate and don't even come close to fully dissolving. The figure on the top right is a medium-sized carbide, 0.8% total carbon, just like the figure on the left. However, it is a soaking temperature of 950 C instead of 850 C, and we can see that we dissolve a little bit more, a little bit quicker. So understanding this initial carbon in carbide is important because it has an effect on the martensite transformation behavior. So the more carbon you have, the more hardenable your material is. So the figure on the bottom left is different carbon levels and the behavior on the MS and the strain. So we can see that as the carbon increases from the orange line down through the blue and the greens down all the way to the gray line, which has the highest carbon, our MS is constantly going lower and lower, and our strain is getting to be smaller and smaller, mainly because too we're cooling a lot further, so we're shrinking a lot more before we start to expand. But understanding this initial carbide in the initial structure is important to accurate heat treatment results. Understood that carbon is rejected from the ferrite as it is transformed from austenite. The DANTE software considers this effect. The figure on the bottom right shows an actual test where it was fast cooled the blue sample and to get 100% martensite. The orange sample was held at a little over 700, forming ferrite, and then quenched. And you can see the effect on the MS temperature, pretty significant here. The figure on the left is from a simulation that looked at 3 different hold times and the effect on MS. And you can see as you hold it longer, we form more ferrite, which then has a significant impact on the MS temperature. This change in MS can have a significant effect on residual stresses and distortion. So any heat treatment modeling, if it needs to consider the carbon rejection as ferrite is formed from austenite in order to have accurate results. The final effect we're going to consider today is the effect of precipitate growth, coarsening, and their effects on material property and volume change. This is all with respect to carbides. So during high temperature tempering or annealing processes, carbides will precipitate, grow, and coarsen. And through this process, the material can actually shrink. The figure on the bottom left shows an essential bell curve of a carbide size versus volume fraction, and is essentially as a function of time. So short times are gray curve, and moving to the right of longer times, you can see how the carbides coarsen and kind of spread their size out. The figure on the bottom right is actual test data of material volume shrinkage due to carbide precipitation growth and coarsening. And you can see there's a significant amount of shrinkage that occurs here from the carbides growing and coarsening. So this is an effect that should be considered if any high temperature hold processes are used, and there is significant carbide possibility. The heat treatment modeling section, I wanted to show a few examples of future requirements that are going to be needed as the heat treatment modeling progresses. First is the computational function development based on experiments from research and manufacturing. What this essentially means is that the models need to continually improve as more and more data is gathered. And with the advent of Material 4.0 and Industry 4.0, there is a push to gather more material data, processing data, which can only improve the heat treatment modeling. Another requirement is going to be understanding the factors affecting phase transformations. This includes the initial microstructure, alloy composition, carbon separation, etc. We learn more every day about what factors really affect the phase transformations and are trying to incorporate these into the model. We also need to look at high temperature tempering due to beyond just a property change, such as the hardness, ductility, strength. There's also material volume changes which occur particularly at higher temperatures. You don't so much see the volume changes at low temperature, so this is more of a high temperature phenomena. There's also the stress relaxation which occurs. We also need to understand the initial carbide decomposing. This has a great effect on the hardness and the hardenability of the material and needs to be more understood. Also need to understand the effect of precipitate growth and coarsening on the material's hardness and strength. And this is particularly important for aluminum and the high temperature tempering steels. Finally, there needs to be an integration of the micro level and macro level material models. This has yet to be accomplished and is a lot more difficult than it sounds, but there is work being done in this area. We'll now like to look at a few case studies. The first case study we'll look at is scanning induction hardening of a truck axle and the main effect of spray quenching on stress formation. The part is approximately 1 meter long with a 35 millimeter diameter, and there's a flange on one end and a 35 tooth spline on the other end. The model assumes symmetry, cyclic symmetry, about one spline tooth. After slicing off the single spline tooth, the surface was meshed with a very, very fine surface mesh in order to capture the high thermal, stress, and phase transformation gradients happening during the induction hardening process. For this project, the electromagnetic phenomena was modeled using Flux 2D, and it was modeled by Fluxtrol. The figure on the top right shows the Flux 2D model with the inductor and the part and temperature. The joule heating profile over the entire processing time was then mapped into the DANTE model, which then predicted the temperature, phases, stress, distortion, and hardness. The process itself consisted of the inductor dwelling at the flange end for approximately 9 seconds. The inductor then moves up the shaft at a rate of 12 millimeters per second for 1.5 seconds. The inductor then slows to 8 millimeters per second as the quench begins. After the inductor is shut off, the spline end is allowed to cool for 60 seconds. The inductor is shut off before ever reaching the end of the spline to avoid overheating. The figure on the bottom right shows the actual inductor and the spray head. This is an animation showing the process as modeled using DANTE. From left to right, we have temperature, austenite, martensite, axial stress, and axial displacement. So you can see as the temperature increases, our austenite is formed, followed by the quenching to form martensite. We end up with a tensile spike that rides out ahead of the austenite, and this can cause serious problems if the inductor isn't shut off before it reaches the end. You can then see that's the ahead of the austenite front. You can then see the high compression that forms on the surface from the expansion to martensite, but you also get very, very high subsurface centerline tension that has to balance out the compression. So 3 different quench rates were examined to see the effect on the residual stresses at the end of the process. The 3 quench rates used were 5, 12, and 25 kilowatt per meter squared C, and they do show a drastic change in surface compression and centerline tension. So the issue with this part was that after installation, the loading on the shaft was causing cracks to develop on the center line of the part down by the flange. And you can see that the baseline, so we assume this is what they were actually using, is a 25 kilowatt per meter squared C. We end up with about 820 MPa down here in the core down by the flange, which is extremely high. You have great surface compression, but if you can't load it properly without cracking the part due to the residual stresses, then the surface compression has to come down some. So all the way down at 5 kilowatt meters squared C, we end up with about 700 MPa, but we also have dropped the surface compression nearly 450 MPa, which is fairly substantial, but the part should survive with this stress level. If you go to the 12 kilowatt per meter squared C, we reduced the surface compression by 200 MPa, but we only dropped the core tensile stress by about 20 to 50 MPa, which isn't very significant at all. So we advise to use the much slower cool rate, which they did, and it reduced the severity of cracking substantially. Next case study I'd like to look at is press quenching of a bearing ring. And the goal of this is understanding process sensitivities during the process. So the bearing ring is approximately 100 millimeter, 4-inch outer diameter, made out of 52-100. And the problem was that approximately 60% of these bearing rings were cracking during quenching and tempering, which is completely unacceptable. So we modeled the process to find out what was causing the cracking and then how to solve the problem. So the figure on the far left shows the geometry and the mesh that was used. This was an axisymmetric 2D problem. The figure in the middle, the two in the middle, show the crack on one of the bearing rings, and you can see a substantial circumferential crack running around this part. Which tells us that the axial stress is what was causing the cracks to form in the first place. The figure on the top right shows a hot bearing ring set on the bottom die of the press quench. So process definition and what we looked at. So we initially ran a frictionless model to start, and the model showed us that they should not be cracking the bearing rings. So it was determined that friction must be playing a part in all of this. So 3 friction rates were examined, a 0.5, 0.2, and 0.05. We also wanted to see what the effect of was if the die is completely stuck. In other words, the part was not free to move, to expand and contract, particularly contract at all. So we looked at fixing the upper die only, the lower die only, and fixing both the upper and the lower die. And fixing the die just meant we held the nodes of the model in place in the radial direction. On top of the quench rates, or on top of the friction coefficients and the sticking conditions, we also wanted to look at the effects of quench rates on the stresses. And this is in-process stress. The residual stresses weren't that bad, but the in-process stress got very high through the friction coefficients. So we wanted to look at what would happen if the quench rate was modified. So we looked at what their baseline was, what we assumed they were doing currently, and then a higher rate, a lower rate. And we also reduced the inner ring rate substantially and kept the outer surface on the outside diameter as the standard rate. So you can see the table in the bottom right shows all our conditions. So we looked at the four different quench rates with friction coefficients of 0.05. We then used a standard flow rate and looked at the three different friction coefficients as well as the three sticking conditions. These plots show the varying the quench rate. So we can see that a standard quench rate, this is with a 0.05 friction coefficient on the top and the bottom die, showed a stress of about 642 MPa, which is high in process, but it shouldn't cause cracking of 52-100. You can see the final stress state, we're at 400, so we do drop some of the tension, but we're still tension out here, which isn't all that good, but it shouldn't crack. Low flow quench rate, we drop substantially. The high flow quench rate, we increase fairly substantially, 100 MPa, all the way up to about 750 MPa, which may or may not cause problems. But then we end up with almost 500 MPa surface tension, which really is not good. So we advised against increasing the rate at all. If anything, we advised to reduce the rate. Reducing the quench rate on the inner ring and keeping the outer ring lowered the stress at the bad location, but it actually increased it down here in these corners. The sticking results. So the figure on the bottom left shows if the top die stuck, and we essentially get the same stress as we did with 0.05. So we assume that the top die sticking didn't have a big effect. Then we move down to sticking to the bottom, and you can see this is substantial increase in tensile stress at the crack location, all the way up to 860 MPa, which will cause cracking. You stick the top in the bottom, and it goes up even more, a little bit more. So the final residual stress is actually a little bit lower than with the friction coefficient being applied. But the in process is so high that this is completely unacceptable. So what we advised was to use the pulsing function that is available on the Gleason press quench machine. This was done at Gleason. So they decided to do that. This is quick animation from left to right, max principal, temperature, and martensite. You can see the high stress comes from the martensite transformation down here in this core. Once that happens, it pushes out on the bearing race while it's trying to shrink. So it essentially tries to straighten out the bearing race, and this is what is causing the cracking. So after they started using pulsing, they reduced the cracking to near zero. They had no cracks after quench, shown in the furnace load 2 and 4. And without pulsing, they were literally cracking exactly 60%. You can see these ridiculously high numbers coming out of quench. So the pulsing fixed the problem. DANTE helped find the problem, and Yeah, so that's that case study. The final case study I would like to go over today is press quench tooling design for a bevel gear using heat treatment simulation. So the bevel gear in question is made out of 9310 carburized. For the model, we used a single tooth of the spline, assuming cyclic symmetry. The bevel tooth on the bevel itself was removed due to the insignificant effect it has on the bore shrinkage, and the bore shrinkage was the main concern for this gear. Figure on the right shows the press quench tooling design set up in the model. You can see that there's a gap between the lower die and the bottom of the bevel. This gap is when the part is cold, and it was maintained in the model. And all dies and expanders are modeled as rigid surfaces, and the thermal interaction between the dies and the part is ignored, which is generally a good assumption unless the contact points are very large or the gear has very low hardenability. So, like I said, the problem here was the shrinkage of the bore. So to understand the effects of the tooling, the first model that gets executed is a free quench without tooling, which is the blue line there. The gray line was their process as it was, with the loads and the locations and the sizes of all the tooling. And you can see that on the spline, the tooling actually made the distortion worse. The upper part of the bore, it made it slightly better, but nowhere near as good as it should be for the amount of effort and money that goes into creating the tooling for the press quench. So what DANTE did was, through our experience, we've learned that plugs can control the bore dimension much better than an expander can. The plugs generally need to be larger than the bore size when they're cold. Once the gear is heated up, then it has no problem slipping over the plug. So that would be the green line then, is the plug. And the plug here we chose oversize of, I believe it was 60 thousandths. So you can see that the plug ends up introducing some taper. But the bore dimension, as far as shrinkage goes, was greatly improved. So much so that the customer was actually happy with this and used the plug to great results. However, we wanted to see if we could improve it further. So the way to get rid of taper is to use the inverse taper in the plug. So we designed a inverse taper plug and executed the model, and that is the red line. And you can see now that the taper is completely gone. The distortion is reduced substantially, even from just the straight plug. However, we were still curious if we could take the contour, the bow out of it that then became apparent. So we designed a contour tapered plug that essentially had the inverse taper cut into the plug. It helped some, but it didn't help enough that warranted the extra cost and time needed to machine a contoured plug. So in this case, the taper plug works very well. So that is using DANTE to design press quench tooling. The final aspect I would like to look at today is the effect of phase transformation on distortion. So this is just using the DANTE model to examine the distortion of point A here in the figure on the right, and looking at radial displacement. So the figure on the left shows the gray line is just ferrite perlite with no phase transformation, and the blue line is ferrite perlite starting conditions with phase transformation. So this is the austenite transformation that happens. So you can see the shrinkage that occurs from the austenite transformation. Then during quench, we get an expansion from the martensite, and we end up with about 160 micron shrinkage of the bore. If we do not have the martensite transformation, then we shrink all the way down to 900 micrometers, which is very significant. That's a big difference between these two. So there is a significant effect from the phase transformation that has to be considered during heat treatment modeling. You cannot just use the thermal strains and assume that your distortion is going to be accurate, because it will not be. This shows the plots of the upper and the lower bores with and without phase transformation, and you can see that it affects both. It's just not that point. It has an effect on the entire size. So with phase transformation, we're about 200 microns, 150 microns. Way out here, we're 900 and 800, 750. So there's a big difference here between using phase transformations and not using phase transformations. So I just wanted to share that with everybody. So that is my presentation. I thank you very much, and you all have a wonderful evening.